all of you know what a fantastic job Faith does in organizing speakers, and tonight,
and you, John, and you. It's not
tonight, no exception. She's organized for Dr. Sam Hatfield from the European Center for Medium Range Weather Forecasting to speak to us tonight. So we brought you a speaker. We brought you somebody to blame for the weather. And
don't blame the messenger.
Sam comes with a first-class degree from Bristol, DPhil from Oxford, and is working at the center I mentioned, which is in Reading. I think, Sam, I'm right in saying it began in 1975, and you have 350 people employed there in Reading, so it's a very substantial institution, and maybe interesting. I don't know whether you'll say a little bit more about that in your talk, but it'd be really interesting to know more about the institution. It's always fascinating for me to learn just how studied the local community here in Oxfordshire, Thames Valley is with these amazing institutions from some time ago. So we are going to hear about extending the weather forecast, the techniques that are being brought to bear on that. And I think, Sam, in your introduction, you said the scope of the weather forecast has been extending by 1 day per decade.
That's right.
Which is an interesting thought. And I think what I should do, what I should have done before, is let you share your screen so you can pick up the trail and take it away.
Okay, I'll try that right now. So, can you see this okay?
Looks good.
Great. Well, if it's okay, then I'll get started.
Perfect. Welcome, Sam.
Thank you. So, so to begin this talk, I want to take us back to October 2012. Hurricane Sandy was a disaster that occurred in October 2012, and it brought powerful winds and sustained flooding across the eastern coast of the US. As you can see here on the right, the storm surge, that is the wave of water that is pushed ahead by the advance of the storm, is often one of the strongest impacts that these storms have on coastal communities. So this storm was a disaster without a doubt. The damages are amounted to around $70 billion in total. However, in some ways, it is actually a success story that demonstrates the value of early warning weather forecasts. You see, there were only around 233 lives lost from Hurricane Sandy, which doesn't even place it in the list of top 20 deadliest Atlantic hurricanes in history. So this relatively low fatality rate was down to accurate long-range weather forecasts, which allowed the authorities to make advanced decisions about, for example, flight and train cancellations and the provision of emergency funding. So in this case, the value of the weather forecast can be measured directly by the number of lives saved, which is likely in the thousands. So over the decades, the quality of weather forecast has become better and better. In fact, the European Weather Centre, which John mentioned is in Reading, that's where I work, accurately forecast the track of Hurricane Sandy 8 days before it made landfall in New Jersey. And here's an example of one of the forecasts that we issued at the time. So this achievement is really the result of decades of sustained research into improving forecasting techniques, including how we build and use supercomputers, how we observe the weather, and how we formulate the mathematics that underpins the weather simulations. And in my field, we like to call this revolution the quiet revolution of numerical weather prediction. And we refer to it as the quiet revolution because the vast improvement in the accuracy of weather forecasts over the past few decades happened at such a gradual pace that no one really noticed it. And it's now something that we very much take for granted. In fact, I believe that had this development occurred over a shorter period of time, it very much would have been worthy of a Nobel Prize. So today I want to take you through the foundation for this quiet revolution, and it's going to be really a mixture of history and state of the art in the field of weather prediction. So I'm going to talk about the history and what further benefits this quiet revolution could bring to society. Now, in order to talk about how we predict the weather, we first have to talk about the technologies that allow us to observe it. After all, if we want to know what the weather is going to do tomorrow, we need to know accurately what it is doing right now. Now, weather observation is nothing new. People have been observing and developing all kinds of folklore about the weather pretty much for as long as there have been people. And although much of this folklore is rather superstitious, for example, I'm not aware of any connection between the tendency of cows to sit down and rain occurring. Some of the proverbs passed down through generations actually do have value even today. For example, I'm sure you're all familiar with the one about the red sky at night being the shepherd's delight. There is actually some scientific merit behind that. And this could be considered a kind of crude, prototypical weather forecast, if you like. Now, observing the weather over a long period of time and noting down recurring patterns, as these proverbs do, it's a good place to start. However, it is, I hope you agree, rather subjective and vague. In order to be more precise, we have to have a way to measure the weather objectively. This quantitative approach to meteorology arguably began with the invention of the barometer in Italy in the 17th century. Barometers measure surface air pressure, which is a very important variable for the meteorologist to observe. And the reason that is because the patterns of surface air pressure determine the strength and the direction of the winds, broadly speaking. For example, high pressure is associated with fair weather and light winds, whereas low pressure is usually associated with unsettled, stormy weather. So beginning in the 17th and 18th centuries, weather stations equipped with devices such as these barometers and thermometers and rain gauges and so on began to observe the weather and record it methodically. And an early example of this kind of weather observing station is the Radcliff Meteorological Observatory, which still operates today using exactly the same techniques as it did in 1772. Some of my fellow students actually volunteered to take that data when I was at Oxford. So over the centuries, the quality of these weather observing instruments have improved, and new platforms have been found to carry them to distant places. For example, up into the stratosphere on weather balloons, or out at sea on weather buoys. And this development reached its logical conclusion with the launching of weather satellites. So these satellites give us bird's eye views of the weather from space, and in some cases allow us to see right through the cloud layers to the surface below. Nowadays, there are always several hundred of these weather observing satellites orbiting the Earth at any moment, constantly monitoring the conditions below. And they became the dominant source of information about the weather and the climate from around the year 2000 onwards. Nowadays, the fidelity of images that we get from these devices is really quite remarkable, as you can see in this example here. This is an animation of one day, or half a day rather, captured by the Japanese satellite Himawari 8, which is in geostationary orbit. It's around 24,000 kilometers away. And as you can imagine, this extremely detailed information is valuable information for the meteorologist. So with the advent of these weather observing technologies combined with radio telecommunications, it became possible for the first time to draw maps of present weather on a continental scale, what we call synoptic scale weather charts. And this mapping process is vital for predicting the weather because weather by its very nature moves from one place to the next. In the UK, for example, with the exception of this week, where we're very much determined by winds from the east, the weather usually comes from the west, from the Atlantic. And so if we want to predict the weather tomorrow, we need to know what is going on over the Atlantic today. And these maps give us this information. So I've just explained to you how we observe the weather and how we come to understand what is happening in the atmosphere at the present moment. The next question is, how do we predict it at the next moment, a few days from now, say? Well, I'm going to explain how this is done by first giving you an example of how it used to be done. And this is what we call the analog technique, and I hope it will become clear why it's called that as I explain it. This is an old-fashioned way to predict the weather. Suppose on a certain day, like February 2nd, that's last week, the weather looks something like this. We have, say, a low-pressure system over Scandinavia, etc. What we want to know is what the weather will be like 3 days from now. So we want to produce a weather forecast. Well, this early technique of weather forecasting is really quite simple. What we do is we consider the weather now, we compare it with a previous occasion that had similar weather in the past. So here's an example from 1986 where the weather looked quite similar to today. In order to produce a forecast 3 days from now, all we do in this case is observe what happened last time and use that as our forecast in this case. So we're essentially assuming that the weather repeats itself. But as we all know, the weather is actually quite chaotic. And so in this case, the forecast failed. What actually transpired was very different to what we forecast. And so the problem with this extremely simple technique is that it assumes that the weather repeats itself, that it is cyclical. But with the exception of obvious examples like the day and night cycle and the seasonal cycles, the weather doesn't simply repeat itself. It is endlessly creating novel patterns that look familiar but are in fact unprecedented. So these two situations on the left here may look similar, but actually they are slightly different. And these differences grow even over just a period of 3 days to give very different outcomes. And so we cannot use this analog technique. It quickly lost its usefulness early on in the history of weather forecasting. Instead, I'm going to present to you how we actually do it using computers. So the alternative to what I just outlined is to predict the weather numerically. And this idea of numerical weather prediction, which is really the state of the art today, was originally developed by Lewis Fry Richardson. Richardson was a scientist, really a polymath who specialized in many different areas. And he developed an algorithmic way for solving the mathematical equations that describe the weather. This is a repeatable method that consists entirely of simple arithmetic, that is, adding, subtracting, multiplication, and division. I'm going to give you a rough scheme of how this works. And I'm going to focus on the specific example that Lewis Fry Richardson concentrated on when he developed this in the 1910s. Let's suppose that we want to predict the change in surface air pressure in central Germany over a period of 6 hours. Well, the way we do it with Richardson's technique is we begin by first observing the weather over the area of interest, in this case, Central Europe, and essentially placing those weather observations on a grid. So we split up the map into these little grid boxes. It's a little bit like an OS map. And then we go through each box one by one, and considering the state of the weather in the surrounding boxes, we use Richardson's algorithmic mathematical formulation to compute what will happen in the next 10 minutes. Then if we wish to produce a 6-hour forecast, we simply repeat this procedure 36 times. It's extremely systematic. Now, Richardson developed this technique, as I mentioned, in the 1910s. And this is essentially the very first numerical weather prediction. And he actually computed this by hand, because this was, of course, the era before computers. And incidentally, he did this while driving an ambulance for the Friends Ambulance Units, which was a kind of Quaker organization attached to the French army during World War I. Because he was a Quaker, he was among the conscientious objectors, and so he was allowed to be a driver instead of a soldier. And in fact, he was so meticulous with his calculations that he did it not once, but twice. And it took him around 6 weeks to compute by hand. Unfortunately, though, although his calculations were actually correct, his very first weather prediction was completely false. He predicted that the surface air pressure would change by about 100 millibars in only 6 hours, which has never been observed in the real world. So his forecast was very much a failure. However, the technique had been proven, and Richardson was confident that with further work in preparing the input data and cleaning it up, he thought a successful numerical forecast could be made. His numerical technique had a more fundamental problem, however, and I've already alluded to it. You see, his 6-hour forecast took him 6 weeks to calculate by hand. Now, in order for a forecast of anything to be useful, you have to be able to create the forecast and communicate it to the parties who are interested in it well before the forecasted events actually transpire. I hope you'll agree that a 6-hour forecast is useless if you receive it 6 weeks late. So to solve this problem, which is really a problem of calculation speed, Richardson imagined dividing up the problem into many thousands of smaller problems, which could be carried out by many thousands of human computers. Now, as I said, this is the day before electronic computers. And so in those days, the word computer actually referred to a human, a person sitting down doing the calculations by hand. So Richardson imagined what we now call a kind of vast forecast factory, which is like a stadium containing many tens of thousands of human computers. And these computers are organized into teams, with each team being responsible for a different part of the globe. In the center here, you can see also a kind of conductor who uses the laser beam to shine on different parts of the globe when we're more interested in what the weather is happening there. And this is quite a remarkable vision, actually, because it's actually surprisingly similar to how a modern supercomputer works. That is, by taking this enormous problem of calculation and dividing it up into many smaller tasks which can be accomplished in parallel. Of course, this forecast factory never actually happened because it's a logistical nightmare. And so there wasn't really much developments in the field of numerical weather prediction for several decades after the time of Richardson. Further developments in this technique had to wait for the development of the first electronic computers. The application of electronic computers to weather prediction was spearheaded by a mathematician called John von Neumann. Now, von Neumann's name crops up all over the place. By this point, the early 1940s, he'd already made a name for himself as part of the Manhattan Project, where he helped to develop the very first atomic bombs. And during that development, von Neumann had noticed that it was extremely useful to have electronic computers carry out the calculations. The particular problem he was interested in was the explosive shockwave generated by a nuclear bomb. And he quickly recognized that this is actually quite a similar problem to numerical weather prediction. And so with the help of the meteorologist Jules Charney, von Neumann established what he called the Meteorology Project. And this was a project whose goal was to produce the very first numerical weather prediction on an electronic computer. So in 1949, von Neumann and Charney produced a series of 24-hour forecasts of the weather over North America. And to do this, they essentially repeated Richardson's technique, but instead of doing the calculations by hand, they used one of the early computers, which was called Eniac. So it was much faster. Now, Eniac, incidentally, is pretty much the ancestor to all of our modern computers and smartphones. And it's quite an interesting testament to just how far computers have evolved in the last 60 years, that ENIAC was just around 100 million times slower than even a normal smartphone today, while consuming around the same electricity as around 60 boiling kettles. So computers have come quite a long way in the last 70 years or so. So these first weather forecasts produced on an electronic computer were actually mostly successful. They were quite accurate. The team were able to produce forecasts over North America, which broadly agreed with the observations of the weather on the actual day. Now, because the ENIAC still required quite a lot of manual operation, for example, in those days, the computer programs were punched in on punch cards by hand from human operators. And because of this, simulating a 24-hour forecast took around 24 hours of time. In other words, their weather simulation was only just able to keep pace with the developments of the real world weather. So it wasn't, strictly speaking, useful for actual weather prediction. However, later generations of computer following ENIAC did away with this tedious manual punch card operations and were able to produce 24-hour forecasts in much less time, thereby becoming actually useful for operational weather prediction. And fortunately, Richardson lived just long enough to see his dream finally realized. He died in the early 50s. So over the next 20 years, computers like ENIAC became an indispensable tool for studying the weather and the climate. And they were adopted by many national weather agencies to produce their regular weather forecasts, such as the Met Office. They even allowed some early research into the effects of increasing greenhouse gas emissions. Of course, climate change was not really part of the national or international conversation at the time, but it was very much on the agenda of climate scientists, even in the 1950s and 60s. It wasn't long before questions started to arise as to the limits of this numerical prediction technique. Questions like, how far ahead into the future can we predict the weather in principle? Was it possible, for example, to forecast the impacts of hurricanes months before they even appeared? To answer this question, we have to introduce an idea called chaos theory. Now, chaos theory is commonly associated with the term the butterfly effect, which really has the same meaning as it does in common parlance in science. The two are very closely related. So the butterfly effect describes how small changes can lead to big consequences. The idea I always like to give, the example, is to think of how different World War II would have played out if Churchill had died in a car accident in the late 30s. Now, in weather forecasting, the butterfly effect fundamentally limits how far ahead we can forecast the weather with any skill. If we could know the position and velocity of every molecule on Earth perfectly, and if we had an infinitely large computer, then yes, in principle, we could predict the evolution of the atmosphere and the weather indefinitely into the future. However, in practice, we cannot know the exact state of the atmosphere at any one time, and our simulations are always inherently imperfect. We do not have infinitely large computers. As a result, even small errors will accumulate and multiply, and within a week or so, render our weather forecasts useless. The discovery of chaos theory is usually attributed to the meteorologist Ed Lorenz, who was working at MIT from the 1960s onwards. Now, Ed was studying a special set of equations, which are fairly similar to those that describe the weather, but much, much simpler. In fact, they only had three variables, what we call X, Y, and Z. So Lorenz, working with a programmer, Ellen Fetter, who, funnily enough, is often omitted from the history, worked to produce simulations of this simplified weather system. And when you plot these three variables in space, X, Y, and Z, you see this rather interesting shape forming, which I think you'll agree looks eerily like a butterfly, but that's complete coincidence. There's no intended relation with the butterfly effect. One day, as the story goes, Lorenz was performing experiments to try and determine the best forecasting strategy for this very simple weather system. Before leaving the office one day, he noted down the values of these three variables, x, y, and z, so that the next day he could come back in, punch them into the computer, and carry on from where he left off the day previously. However, the next day when he did that, he found that the simulation produced a very different outcome to what it did the day before. Puzzled, he inspected the input that he had just put in and realized that actually it wasn't exactly the same as the one on the day previously, because when he wrote down the values, he rounded them to 3 decimal places, even though the computer works with 6. So he had rounded those numbers thinking that those 3 small, least significant decimal places wouldn't matter, but actually, in this case, they were key. And simply omitting those 3 digits led to a very different outcome in the weather forecast. So this accidental experiment demonstrates that even small differences in the initial conditions of a weather simulation can give dramatic differences in the outcome. So the implications of this simple experiment are actually huge. What it means is we could build vast computers, cover the surface of the Earth with sensors of pressure and temperature and wind, etc., and fill the sky with weather observing satellites. But if we miss even just the fluttering of the wings of a butterfly in our simulation, then our forecast will ultimately fail, and there is no way around this. Lorenz demonstrated that there is an ultimate limit to the predictability of the weather, what you can think of as a horizon beyond which we cannot see, no matter how sophisticated our technology. Now, exactly how far out we can actually predict the weather in an ideal world is currently a point of contention, but a rough estimate would be around 2 weeks. So even though there are limits to the predictability of weather, that doesn't mean that weather forecasting isn't useful to us. Indeed, over the past few decades, an enormous public and private industry has arisen from the developments that I've outlined today of Richardson, von Neumann, and Lorenz. And these technologies allow us to forecast hurricanes, for example, well in advance, like the case of Hurricane Sandy. So although chaos will ultimately prevail, we can at least tame it. Now, just how much have weather forecasts improved since the invention of the numerical techniques, which I just explained? Well, this graph gives us, well, not the answer, but certainly one of the answers. This is a graph produced by my employer, the European Weather Centre. And this graph essentially shows us the skill of weather forecasts over the past 4 decades. So you can see on the x-axis, we begin at 1980 and we end at the present day. On the y-axis, we have the accuracy of the weather forecasts according to a very specific measure, which I won't go into details, but suffice it to say, this is generally accepted to be the best way to measure the skill of weather forecasts. Now we have 4 colors, and each color represents a different lead time. So blue represents 3-day weather forecasts, and pink, green, and yellow represent 3, 7, and 10-day weather forecasts. Now the yellow 10-day weather forecasts are always lower in skill than 3-day weather forecasts. That's because it's harder to predict the weather the further out in time you look. Now there's one other thing you might notice here, and that's that there are 2 lines for each color. The top line is showing us the skill of weather forecasts in the northern hemisphere, and the bottom line shows us the skill in the southern hemisphere. You might notice that there's quite a large gap, at least back in the 80s and 90s, and that's because in the southern hemisphere, at least back then, there are far fewer observations because there's less land. But really that gap between the north and south has narrowed quite dramatically from the 2000s onwards because satellites came around, which of course observe the whole Earth uniformly. Now the take home from this graph is that the skill on all timescales has improved over the last 4 decades, quite a bit in fact. If you were to compare the skill of 7-day forecasts today, you could see that it's actually about the same as the skill of the 3-day forecasts in the mid-80s, at least in the southern hemisphere. In other words, with each decade of development, we are able to peer one extra day into the future. This is the 1 day per decade quote that John alluded to at the beginning. So that is where we are now. That is the state of the art in medium range weather prediction, that is up to 10 to 15 days. But the technologies created for weather prediction provide value for many other forecasting problems as well. For example, seasonal forecasts are a new and rapidly developing area of weather prediction. These forecasts aim to give us a general outlook of the weather conditions over the next few months. So we're looking well beyond the 15-day period that's usually considered to be medium range. Now, although I mentioned earlier that the weather never repeats itself, that is the day-to-day weather, there are, in fact, underlying the weather, much larger, slower patterns, which vary on a seasonal timescale. These include, for example, the warming of surface waters off the coast of Peru, which is called the El Nino, the El Nino oscillation, which you sometimes hear about in the news. This is basically a periodic warming and cooling of the waters in the Pacific that occurs every 3 to 4 years. So seasonal forecasts basically aim to identify the global weather conditions that are usually associated with these relatively easily predictable recurring patterns. Although there is still very much work to be done on these seasonal forecasts, they could one day provide crucial advice for farmers in India, for example, who may decide to plant different crops depending on the outlook for drought or flood. And by the way, you might be wondering whether this contradicts what I said earlier about there being a fundamental limit to the prediction of the weather on 1 to 2 day timescale. Well, if you like, you can think of the difference between these large scale patterns and the day-to-day weather as similar to the difference between the tides and the waves. We can't predict the exact waves. They're very small and choppy and very energetic, but broadly speaking, we can predict the tides because it's a much larger, slower pattern. And that's really the kind of pattern that seasonal forecasts are trying to identify in the atmosphere. Additionally to these weather forecasts, the world's plans for mitigating climate change are crucially dependent on projections of temperature increases made by simulations of the future climate. These climate simulations are built on essentially the same technology as weather simulations, the difference being that they cover many decades into the future, and they are, as a result, fairly lower in spatial resolution. If we didn't lower the resolution, they would be too expensive to run on our computers. So every few years, the world's climate scientists all around the world run simulations into the future which assume different concentrations of greenhouse gases like carbon dioxide. And they collate the analyses of these experiments into the periodic reports of the Intergovernmental Panel on Climate Change. And I believe there'll be one of those reports coming out either this year or next, in fact. And some of the results are shown here. This is an example from the previous reports. What we're looking at here is essentially a projection of global surface temperature change into the future up to the year 2100. So the white line is what we've observed. This is what actually happened between 1900 and 2000. And everything to the right of that is a projection into the future. Now, we use the word projection instead of prediction because we don't actually know how society will evolve in the future. We can't predict what the proportion of fossil fuels will be in the energy systems of 50 years from now, for example. But what we can do is assume that fossil fuels will evolve in a certain way, and from that, try to figure out what the associated temperature response would be. And we call these different emissions scenarios. So for example, the RCP 8.5 scenario is really the worst case one. This is where fossil fuel use continues to accelerate. And in this case, we can see that although there is quite a wide spread indicated by this line, this red line on the right, we should see around a 4 degrees increase in temperature by the year 2100. On the other hand, if we assume a much more optimistic future trajectory, what we call the RCP 2.6, we can see that we'd only get around 1 degree warming in the future. Now, there's a fair amount of spread between these models. These bars of uncertainty on the right are quite wide, indicating that the models do somewhat disagree with each other about just how much warmer it will get in the future, even for a specific emission scenario. But the models are very much unequivocal in the fact that the world will get warmer. They just disagree about exactly how much and exactly where. So in the future, developments in numerical weather prediction will likely be transferable to this problem of climate prediction, giving us more detailed insights into the future climate. So what does the future hold for weather prediction? Well, we will continue to peer further and further into the future, stretching towards that insurmountable barrier that Lorenz discovered in his experiments. By 2050, we will probably be able to predict the development and evolution of hurricanes, like Hurricane Sandy, up to 10 or 11 days before they even appear. Every extra day of skill that we can squeeze out of our forecasting systems provides immeasurable benefits in terms of early warnings and evacuation notices. As we do this, as we push further and further ahead, we will find that we need to simulate not just the atmosphere where the weather actually occurs, but also the oceans whose warm water fuels tropical storms. Not to mention the sea ice at the ice caps, whose mirrored surface reflects sunlight, thereby cooling the surface air. And we will probably even have to consider the biosphere, that is, the living organisms of the Earth, like the tropical rainforests, who can actually seed clouds. And so in order to predict the weather, we also need to know about these kind of biological processes. So gradually we will move towards what we now call an Earth system approach, which is more like a kind of holistic approach towards the full planet Earth prediction problem. Weather and climate prediction, which are usually considered separate disciplines, will be, I think, fused together into what we call seamless weather and climate prediction. So to finish my talk, I want to share with you an example of the state of the art in weather simulations. And this is an example taken from my employer, the European Weather Centre. On the left, we have an image of the Earth captured by a weather satellite, Meteosat. And on the right, we have a visualization of a simulation of the Earth, which was initialized 4 days before the photograph was taken. So it's a 4-day forecast. And I hope you agree that just by comparing these two, just by eyeballing them, you can see that there are the forecast is strikingly accurate, particularly in the mid-latitude regions around Europe, for example, where there is quite a strong correspondence between the patterns of the clouds. Nevertheless, there are clearly differences, particularly in the tropical areas around the equator. And so there is still very much plenty of development to be done in the future. So the challenge for the next generation of meteorologists, including myself, will be to further harness the power of mathematics and computers to bring our forecast simulations more in line with reality, thereby allowing society to adapt itself to the extreme weather of a changing climate. So that is where I'm going to end. And I think I'll take some questions now, if there are any. So thank you for listening.
Sam, hey, really nice job. Thank you very, very much indeed.
Thanks.
Really interesting and very rounded presentation. By the way, having my middle name Shepherd, the Shepherd's Warning piece played right to me, and in fact, I guess one of the sorry, I'm losing the plot a little bit with the questions coming in. In fact, if Faith is on
Yes.
call now too, I think the moment, Sam, you mentioned the phrase climate change, there was a question from Mike Landy arrived back in the chat box.
Mike has given a talk on climate change before, and so is pretty well versed in this. But he's
I see.
what was it that? Sorry, it's just moved out. What was it that caused the recent increase in the Met Office modelled temperature increase this century? What
was it that caused the recent
increase in the Met Office models temperature?
I'm not sure what Mike's referring to there.
No, maybe we need Mike to we can unmute Mike to perhaps elucidate.
Perhaps he may be talking about the latest round of climate simulations which were carried out to support the new IPCC report, which the Met Office does participate in.
Yes, that's right.
You can clarify.
Can you unmute? Oh, you have. Yeah, Mike.
Yeah, that's correct. It was the forward simulations, and
yeah. Am I right in thinking that this could be an area where you know more than me, actually, because
no,
I wasn't aware of which which specific models, but I did hear that some models in these among these new state-of-the-art simulations did exhibit a stronger sensitivity to carbon dioxide concentrations to previous ones. In other words, yeah.
It did bring the Met Office model closer in line with all of the other ones.
Right. Honestly, I don't actually know. I don't know what would have caused that. But you know, I'm sure the jury probably still isn't out. What I do know is that it's extremely difficult sometimes to build up a chain of causation, which gives you a satisfying answer as to why the models behave in this particular way. But I'm afraid I don't actually know the answer in that specific case.
By the way, mention of the Met Office, can I ask a kind of, or segue to a question that faced? You and I came across an understanding that the biggest computer in this country is the one parked in the Met Office at the moment.
I think that is correct. Yeah, it cost around £90 million a few years ago. But actually, it's still kind of a small fish on the global scale. You know, it's very much useful for us, don't get me wrong. But supercomputing it's become quite ridiculous, actually. It's almost become like the space race, where the UK is somewhat struggling to make itself known among the Americas and the Chinas and the Japans. But yes, we do have a fairly big computer in the Met Office, yes.
And that chimes exactly with my recollection of this the sort of stat we stumbled across, because it was a list of a ranking of supercomputers around the world, and if I remember right, it was we came in at number 37, but it so happened it was the Met Office that had the one.
Yeah, I think that's true.
The Met Office, I think the best the Met Office got with their latest system, which is still pretty good, was about number 10, if I recall correctly. Yeah. Okay. The largest system currently is in Japan.
Interesting.
Okay, well, let's move on to the next question. There's one from Stephen Burke. My memory is that clouds aren't simulated directly. Is that still true? Do you know about clouds?
Yes, broadly speaking, that is broadly true, yes. So when we see a cloud, we think of it as quite a large object. But from the perspective of a global weather simulation, clouds are actually considered to be small-scale features. Of course, it depends on the cloud. The most important clouds for weather prediction are probably cumulus clouds. These are the very pretty ones that you can see when you're taking the train between Reading and Oxford on a sunny June day as you look out over the Chilterns. These are extremely important, especially in the tropics, where they can go up to 10 kilometers high. They are too small to be resolved by current state-of-the-art weather simulations. And that is because these weather simulations have pixel sizes, if you like, of around 9 kilometers. And so that's still relatively big. And so anything smaller than that cannot be resolved by the model. That doesn't mean that we ignore them. Instead, what we do is we simulate the collective behavior of those clouds as that is exhibited over a 9-kilometer scale. So we basically average all of the different cloud behaviors over that 9-kilometer grid box, and we feed that into the weather model instead. However, there is quite an exciting development which will probably happen in the next 5 to 10 years in our operational model, which is that we are currently developing a 1-kilometer resolution simulation, which is really quite a remarkably high resolution simulation of the Earth. When you see it visualized, it really does look like the real thing. It's virtually impossible to distinguish it from reality. And those simulations are actually high resolution enough to resolve these clouds. And so we will be able to resolve them for the very first time instead of relying on these averaging functions that I just mentioned.
Sam, that's a wonderful sort of concept. It's like an oxymoron, a pixel size measured in kilometers.
Yeah, exactly. And there's a term that's come over the past few years, what we call the Turing test for climate, which is if you can't tell the difference between the simulation and reality, that is the point at which you can rest, because at that point the forecast is not going to get any better.
Okay, the next question is, what's the main limit on your ability to forecast at present? Is it computing power or is it something else?
It really depends who you ask, and it depends on the particular forecasting problem. Really, my entire research and career is predicated on the fact that, yes, we are limited by computing power. What I do day to day is to try and squeeze as much performance out as possible out of our supercomputers. And the assumption that relies on is that that extra computing power can be put to use to improve the weather forecast. Generally, that is the case. When we get a computer that's twice as fast, we get a more higher quality weather forecast because we are able to invest those extra resources into more resolution here, more resolution there, etc. But generally speaking, improvements anywhere in the forecast will manifest themselves as higher quality weather forecasts. So if we, for example, there's a new state-of-the-art satellite, well, actually, I think it's actually already been launched, which observes tropical winds in unprecedented detail. And that, for example, is expected to deliver a substantial increase in weather forecasting skill. So really, there is no, I wouldn't really say there's any specific area that's limiting everything. Really, every little helps.
Okay. Another question, is ECMWF looking at quantum computing? We're hoping to get a talk on this later, actually, aren't we, John? I think in a few months' time, we're going to have a talk on the new quantum computing centre at Harwell. But anyway.
You read my mind, actually. I thought that's a perfect platform for a shout out for our speaker in 2 months' time. A gentleman called Simon Plant, who's Deputy Director of the National Quantum Computing Centre, which is it's in the design stage and probably a year or so before it's actually built on the Harwell campus. So I guess, Sam, you'll be one of their network customers, contracts, whatever.
Yeah, I think we certainly have an interest in quantum computing. As far as I'm aware, there's no internal efforts to conduct research on quantum computers, but we certainly are. I would say we're at the stage of reaching out tendrils to various startups which are trying to make actual practical quantum computers. So I would say that we're interested. Yeah, but we're certainly not expecting to have a quantum computer operationally in the next, 10 or 20 years at least.
No, but there is actually one on your doorstep in Reading now. And
is
that's
that right?
Oxford Quantum Circuits, who claim to have the first quantum computer in the country. Sadly, they're not on the Harwell campus. They were in a bit of a rush, and they opened a new lab on Reading, on Thames Valley Business Park in Reading. So,
oh yeah, yeah,
go bang on their door. They'd love to see you, I'm sure.
yeah. I'm sure we should get them in and really see if there can be any use for these things for weather simulations. I think that'd be really fascinating. It could be, yeah.
Okay,
Crash the question.
Next question. This is an interesting one because, yes, there was quite a difference about the weather forecast last night, actually. Ian Cameron says, if weather forecasting is improving, what is the reason for the BBC app forecast often being different from the Met Office one? Sometimes they can be very different. Yesterday, the BBC said there was going to be heavy snow and the Met Office did not. Actually, the Met Office was right, well, in this area, that is. So,
yeah. Oh, that's a very good question, because probably I should first explain that the sector I work in really doesn't engage with ordinary users. Our users are large, well, there are other governments, for example, and also things like large logistics companies and aviation companies, things like that. And that's really a different kind of customer to the everyday ones like us. And the Met Office and the BBC have quite a different problem in communicating with the general public, because they don't want to be, bombarded with enormous weather charts. They want to see a quick and easy to understand representation of what's going to happen in the future. My understanding is that this is still very much an imperfect process. The Met Office and the BBC will take different decisions about which information they choose to withhold. For example, I'm not, as far as I'm aware, the BBC still do not show any real kind of probabilistic information about the weather. I could be, correct me if I'm wrong, but they don't show it. Well, they might show it for rain, but I'm not aware that they show it for anything else. And this could explain the differences you see, because sometimes the weather is just very hard to predict. And in those situations, the most accurate, the most honest forecast is one that is honest about the uncertainties. So, yeah, I think the best answer I can give is that different companies have different ways of packaging the data, and some of them don't present all the information that they should do. And if they did, you would see that actually they're much more similar than they appear.
Okay, yeah. Moving on to another question. There's a recent report from the Geophysics Research Letters showed that the lack of global transport movement during COVID-19 has led to an increase in global temperature due to decreased aerosols, leading to increased solar input. How will climate models deal with these unforeseen events, if that's the case?
That's a very good question. Things like pandemics, I think that's in the realm of events that it's quite reasonable that climate scientists would not be able to predict. And of course, those have sometimes quite significant impacts on the climate. Probably it will be dealt with the same way that volcano eruptions are dealt with. Volcanoes, for example, the Pinatubo eruption, which occurred 1989, they spew enormous amounts of sulfur dioxide aerosols into the climate. And we typically see a decrease in global temperatures of 1 or even 2 degrees over a 1 to 2 year period. This is the kind of thing that cannot be predicted by a climate model in advance. However, when we go back and rerun over the weather that's already occurred, the past climate, we do have ways to insert those volcanic eruptions into our simulations. And my guess is that in the future, when climate scientists go back and repeat forecasts, hindcast, if you like, over the past, they will probably have some factor to account for the significant drop in aerosol emissions. That is my guess. And if they didn't do that, then how could they guarantee that they're simulation would have any accuracy going to the future.
Thanks. Could I, forgive me, take you back to the last question about the difference between the forecasts?
Yes.
And I'll ask Sam a personal question. Sam, when you're deciding whether to put a raincoat on or take an umbrella, which forecast do you use?
Well, this is maybe the embarrassing thing, which is that over the next hour, honestly, you'll have a better time just looking at a radar image. So even now, they are still usually, that's not a forecast, that's just looking at the weather and using your eye to predict where the clouds will move over the next 30 minutes to 1 hour. So actually over the period of 1 to 2 hours into the future, it is still actually generally more accurate just to assume that rain clouds will continue moving in the direction you've seen them move in the last half hour. Weather forecasts only really have value for timescales over 12 or 24 hours. So yeah, to answer your question, I usually look at the radar on the Met Office app. Maybe I might wiggle the timer back and forth so I can see where the clouds were half an hour ago, where they are now. And then I just sort of eyeball that and basically guess where they're going to be in the next 10 to 20 minutes.
Okay.
And based on that,
So you're kind of saying the whether man or woman on the BBC isn't lying?
Not not necessarily. Well, what I'm saying is that up to an hour, this, by the way, there's a name for this. It's called nowcasting. It's a bit of a stupid name if you ask me. Is generally more accurate than forecasting. Nowcasting basically assumes that the winds will stay in the exact direction and strength they currently are, and therefore things will just continue moving in the direction they're currently moving into the future. It's a very simple extrapolation. There's no numerical model or supercomputer involved. Generally, that is still more accurate than the models over a period of 1 hour. So that's what I look at.
There's a comment from Ian Cameron here
yeah.
saying he uses the radar image on the Met Office app.
Yeah, it's brilliant.
Yeah.
It's really brilliant. Yeah.
Okay, that's.
I think it's on Windy as well. If you know Windy.
Yeah. Question from Ian Jones. How much of the improvements in forecasting come from sensitivity studies, also known as an ensemble forecasting?
So I should briefly explain on ensemble forecasting, because I skipped over this, even though it's actually quite a significant development in the last 30 years. The idea of ensemble forecasting is to basically repeat the forecast many, many times with slightly different input parameters, with the hope that when you consider all of those, what we call ensemble members collectively, the truth of what actually will happen will be somewhere buried in that ensemble. It's a bit like it's a more kind of democratic way to predict the weather by taking a vote between many different simulations. And they have a number of uses. For example, well, basically what you outlined there, by looking at these ensembles, we can see the kinds of weather features that generally occur on average, given certain starting conditions. And so they are very much a useful tool, not just for forecasting the weather, but also improving weather forecasts. Yeah.
Thank you. We've got quite a few questions from Colin. I'm going to have to filter these a bit but anyway, moving to Chris Baguli. Does the 11-year sunspot cycle have much bearing on weather forecasting?
Honestly, I've been in this field for 7 years now, and I've never heard it mentioned. So my guess is probably no.
Okay.
But you would be surprised when you dig into the code. You often find these obscure things turning up somewhere. For example, we do have an ocean simulation, and in fact, that ocean does actually account for a geothermal heating at the bottom of the ocean. You wouldn't expect that to have an impact on the weather. It probably doesn't, but it is in the simulation. So I wouldn't be surprised if somewhere buried in our system somewhere there is actually a sunspot cycle. But that's a whole other kettle of fish, because it's not really, as I understand the sun, it's not entirely regular. And so then that brings the question of whether you need to also have a sun simulation. But yeah, as far as I'm aware, there is no real link between sunspot cycles and and weather forecasting.
Okay, here's one from Colin. What's the proportion of data input to models from satellite and surface measurements? The Radcliff weather station suffers from the same problems he's seen throughout the world: urban, poor exposure, and very local ground level measurements.
Yeah, I'm not sure the numbers off the top of my head, but I can say that satellites provide most of the, well, they'll provide not just most of the raw data, but also most of the useful data. Not all weather observations are useful. For example, if you have two weather stations right next to each other, they're pretty much redundant because one, they'll just agree all the time. Yeah, I honestly don't know off the top of my head what proportion of the input comes from satellites, but it is the majority.
And then this final question, unless anyone else has got anything. Has the reduction in aircraft flights reduced the amount of data? Oh, sorry, it's moved. Sorry, I've lost the question. Has the reduction in aircraft flights reduced the amount of data you use for your models?
Yes, it has. And when we come to creating our annual reports on the quality of our predictions over the last year, I do expect to see a dip in the skill when the pandemic started. Aircraft are what we call observations of opportunity. So the aircraft operators, through goodwill, carry around weather observing observations for us. And those are actually quite a useful source of weather information. As you can imagine, they go right from the ground up to the stratosphere. And that was cut down by, a good 80 or 90% in March and April last year. It's kind of gradually gone back up a little bit since then. I think it might be actually that some weather centers around the world decided to launch more weather balloons to try and compensate for this. So the impact will not be quite as bad as we expect, hopefully. But yes, I do expect to see a dip in the quality of the forecasts for 2020.
Thank you. Just apologies to Bryce, I did miss his question. He asks, what sort of organisations value most the work of the ECMWF based on the assumption that value is measured on how much they are willing to pay for the forecasts?
Yeah, so as I mentioned, our users are large organizations, not individual people. That's for the honest answer is because they're generally too expensive for ordinary people. So our customers are, big shipping companies, but also other national weather agencies. They're probably our main customer, to be honest. Whether we get revenue from them or not, I'm not entirely sure. But yes, those are the people we have in mind when we create our weather forecasts.
Your funding is EU funding, is it?
Actually, no. We are separate to the EU, so we actually predate the EU, or I'm not sure what it was called back in the 70s, but we predate 1975. Basically it was before whatever the current form of the European Union is at the moment. So we're more like an international treaty organization, analogous to the European Space Agency, or perhaps the European Patent Office. So we are actually separate to the EU, but we do still bid for EU science funding, which sadly is somewhat jeopardized by Brexit. And in fact, to respond to that, we're deciding to open a new center in Bonn, which is where all of our EU funded activities will be based in the future.
Okay.
But Sam, in a way, that's the best news we've had all day. There's no Brexit for the weather.
Well, exactly. I mean, weather does not respect borders. And I think it's, sorry, go ahead.
No, I was just going to say 50% of the audience probably disagree with me, but referendum story.
Well, I mean, it's, it's a nice example of, I'm not going to, say it's a European thing in particular, but it is an example of how cooperation among smaller member states can really work, because the European Centre is basically the best in the world at what it does. And I think for that, we can thank the fact that we're able to attract people from all over Europe to focus on one particular problem, that is trying to predict the weather over 15 days. So when you have a very specific goal in mind that everyone can rally around, then that's exactly the kind of problem that is very amenable to international cooperation.
Well said. Well said.
Mike Landy has offered to come back actually on his question before. If you could unmute
Okay.
Mike, John, just to clarify his question.
I've asked him to unmute, but Mike, can you tune in?
Self.
Oh, there he is.
Yes.
Yes. What it was is that the Met Office announced in mid-December that it was the warming that has occurred since pre-industrial times that they have revised upwards by almost 0.2 of a centigrade.
Okay, so basically, previously we thought that global temperatures had increased by about 0.6 from 1850 onwards. And now they're saying, actually, we underestimated that. Actually, the world has got 0.8 degrees warmer. Is that correct?
Yeah, the figure that I've seen quoted is now 1.07, actually.
Oh, okay. So it's beyond the 1 degree mark. So that really shows the problem, really, because we don't even know by how much the world has already warmed, yet alone how much it will warm in the future. All of these things are very much laden with heavy error bars.
Okay.
Faith,
Yeah.
can I just add in one point and maybe put to Sam? Sam, I have a one particular interest in cryogenics, low temperature technology, and within Oxfordshire we have a fantastic concentration of cryogenic expertise like nowhere else in the world, through accident of history, but in the 1990s, with technology shared between Oxford University and Rutherford Appleton, what was called the Oxford cooler, a cryo cooler, if you like a refrigerator, very low temperature refrigerator. Prior to that development in the 1990s, Earth observation satellites were sent up with a bucket of something cold like liquid nitrogen or liquid helium to cool the detectors to give the same principle as they actually use in the is it Hawkeye camera in cricket? No, the Hawkeye's Wimbledon. It's sorry, whatever they use in cricket to capture the little nick of the ball on the bat or the wicket. The Oxford cooler became the most successful cryo cooler technology flown in space by a country mile, and so it displaced people sending up satellites with a bucket of, like I say, probably liquid helium to cool detectors. And my amigos in that sphere claim they revolutionized the weather forecast from that moment onwards by something up into space that would run and run and run. If it was a bucket of liquid helium, when it evaporated, game over, satellite defunct. But the cryo running on solar power would run and run and run and run. And that was what the technology was all about. They were just amazing bits of machinery. So little shout out for cryogenics in the scheme of making better weather forecasts. I don't know whether you buy that or not.
Well, yeah, I mean, I wasn't aware of that problem actually, but it's kind of a funny problem to have, isn't it? Because you think of space as being extremely cold. I mean, it's only what, 2.7 Kelvin, but I guess when you're exposed to the sun several hours a day, it does actually become a serious issue in keeping the data clean.
I guess that's part of it. I tell you what, I'll find something to share offline. But
Okay.
given a chance to talk up cryogenics, I'm afraid I can't miss that.
Yeah, that's fascinating. Thanks.
Hey,
Right. I think we're nearly at
I think you've done fantastic, and we've really got a lot out of you. Talking for over an hour, and a fascinating talk, Sam. Thank you, really sincerely. Thank you very much from all of us
Thanks for the invitation.
and for dealing with all these questions so thoroughly as well. I think it's fantastic.
No, I'm always surprised by just how detailed the questions go. I mean, people really know their stuff.
That's Wantage for you. Be warned.
Yeah.
By the way, I think there is another shout out. Some folks on the call may recall a gentleman called Tristan Gooley, sometimes known as a natural navigator. He can tell you what direction he's pointing in, north, south, east, or west, by looking at the bark on a tree or in the sky or whatever. But he gave a talk at the Wantage Literary Festival probably a couple of years ago, Faith.
Yes, I think it was
and
yeah.
I think he is at launch stage right now with a new book called The Secret World of Weather. So I'm assuming Tristan, Natural Navigator, is explaining to people how they can tell whether they need an umbrella or not by sniffing the air or watching the birds or whatever.
Or the cows.
The cows, yeah.
The cows. Fantastic.
I'm sure there's a scientific.
Yeah.
We gave a little bit of a shout out for the Quantum Computing Center talk in 2 months' time, but we have another talk in 1 month's time, Faith.
Yeah, actually, I think the quantum one is 3 months' time, John, because I think we've got so next.
Oh, you're right. It's May.
Yeah, we've got Sally Pawlowski next month talking about Oxfordshire's Living Laboratory, which I think is some sort of collaboration, public-private collaboration, looking at new technologies to support sustainable living. And I don't know more about it than that. Hoping to get a bit more information from her soon. And then the following month, we've got Hugh Warwick talking about hedgehog conservation, maybe other wildlife as well. And then we've got the quantum computing one. So that'll be May, actually. Lots to look forward to.
Well, indeed. And if we're done, just to say huge thank you to Sam. Thank you so much to Faith for organizing this. And thank you all so much for joining us.
Yeah.
Absolutely.
Yeah. Thank you, Bryce, for that message. Yeah. Thank you.
Thanks.
Okay. Thank you very much, Sam.
See you soon.
Yeah.
Keep warm.
Okay. Thanks a lot.
Bye-bye.
Bye-bye.
See ya. Bye. Thank you very much.
Thanks, Sam. Thanks a lot.